Welcome to ConcreteSection. In this video, we'll explore how the software's analysis engine works to determine the section's capacity and to compute stress results under applied loads. Let's get started. ConcreteSection performs two distinct analysis tasks. First, it generates the three-dimensional interaction surface on the Surface tab. Second, it computes the stresses and strains under specific applied loads on the Stress Results tab. Both tasks rely on three mechanics of material principles: strain compatibility, material constitutive models, and equilibrium. Before we dive into how ConcreteSection applies these principles, let's look at the fundamental behavior of reinforced concrete itself. Reinforced concrete behavior. Reinforced concrete combines two distinct materials, concrete and steel, with fundamentally different mechanical behaviors. Concrete is strong in compression but weak in tension, while steel provides reliable strength in both tension and compression. Capturing their combined response requires enforcing strain compatibility, applying accurate stress-strain constitutive models, and ensuring force equilibrium throughout the mesh of the cross-section. Strain compatibility. The assumption that plane sections remain plane means that the cross-section does not warp during bending. This results in a linear strain distribution throughout the section depth. Additionally, strain compatibility assumes a full bond between the steel and the concrete so that both materials share the same strain at their interface. ConcreteSection divides the cross-section into a triangular mesh and computes the strain in every node using these fundamental assumptions. Material constitutive models. The analysis engine uses the material constitutive models to translate the strains in the cross-section into their stresses. In ConcreteSection, steel has elastic, perfectly plastic stress-strain relationship for both tension and compression as shown in the image. In ConcreteSection, concrete is assumed to have no tension capacity. In compression, the stress-strain relationship is nonlinear as shown in the image. The concrete compression stress-strain behavior is defined using four key parameters: the strain at maximum stress, epsilon naught, the ultimate strain, epsilon u, the maximum stress factor, K, and the confinement factor, gamma. The maximum compressive stress, F double prime C, is calculated as K times F prime C, where F prime C is the specified compressive strength. This maximum strength occurs at epsilon naught. At the ultimate strain, epsilon u, the stress is reduced to F double prime C times the quantity of 1 minus gamma. Note the failure strain, which is the strain in the section's extreme fiber when the section reaches full capacity, can be set to either epsilon naught or epsilon u in the program. This setting affects the calculated section's capacity, effectively shifting the bounds of the interaction diagram. Equilibrium. The principle of equilibrium requires that internal stresses in the concrete and steel balance the externally applied forces and moments on the cross-section. In ConcreteSection, the software enforces this by numerically integrating stresses over each triangular element in the mesh to compute the resulting internal forces and bending moments. Putting it all together, the interaction surface shows the capacity of the reinforced concrete section for every combination of axial force and bending moments. Given the concrete failure strain, the neutral axis offset, and the neutral axis angle, ConcreteSection calculates a capacity point on the interaction surface. ConcreteSection then loops through a variety of neutral axis offsets and angles to generate the entire surface. For the stress results, the analysis engine finds the state of stress and strain across the section that is in equilibrium with the applied axial force and bending moments. This problem involves solving a system of nonlinear equations. Mathematically, this is an optimization problem where ConcreteSection finds the combination of neutral axis offset, neutral axis angle, and strain that minimizes the difference between the integrated stress over the cross-section and the applied loads. Together, ConcreteSection's analysis engine provides both a global capacity overview of the cross-section and a detailed local stress-strain response under specific applied loads. That wraps up the theory behind ConcreteSection's analysis engine. For more information on the inner workings of the program, be sure to check out the help file, which is accessed by clicking the button in the ribbon. Thanks for watching and have a great day.